And we're good. Hello. Good morning, everyone. Welcome to the first Venice. I'm Michele Mauro. I usually talk about myself saying I'm a passionate developer. I usually write in Java, Scala, and sometimes other languages. And I work in Aton. Today, I'm going to talk about my experiences. I'm not presenting something validated from science, but I'm talking about something that I did and something that I discovered that I think may be useful for you to know. Okay, show of hands. How many of you have an event sourcing application in production? We have one, too. Yeah, great. How many of you have an event sourcing prototype or have evaluated one? Some more hands. How many of you know what event sourcing is? Okay, for the rest, for these people, just a bit of patience while I explain to the others what event sourcing is. Okay, let's start. This is a story about a system that I built with some of my colleagues, and we built it in a particular way, and now we're talking about why we built it. The key word where I worked was modernizing. We had a working application that served several clients. However, there was some problems. Yes, it worked very well. It was not your typical Java monolith because it wasn't a JEE application, but it was written in Java, and it was, in fact, a monolith. In fact, we had the problem that it didn't scale, both in iron and in people. It was becoming difficult to find people to work on such a peculiar technology. It was one instance per client. Whenever we get another client, we have to set up a completely separate stack. And I have to confess, the code wasn't very good. It was becoming a big ball of mud. So we went for a rewrite. That's not a decision you need to take with a light heart, but it was the right thing to do in that situation. And so we built an event sourcing system. We built a system where commands came in from one side, events got written in the middle, and then queries were served from the other side. Why we built it that way? You can find online lots of tutorials that explain you that an event sourced system is easy to scale, is easy to reorganize a microservice if you need it. It's easy to adapt to changes that you can predict in advance. And it's easy to process multiple tenants on the same systems. That were all abilities that we needed. That's why we choose event sourcing. And we wanted those abilities. With some work, we got many of them. And we got the system to work. Okay. Event source systems usually don't go alone. It's a characteristic of the event source system that its state is not easy to query. So usually, if you don't have the use case to search inside your system, then you're good. But if you have it, it's not a difficult problem to solve. You just need another abstraction that is called CQRS, Common Query Responsibility Segregation. This pattern goes usually in, together with event sourcing. Let's see what it is. A CQRS system is made of two parts. The first part is the command part, also called the write side, that accepts commands from the outside, evaluates them, and if it has accepted the command, the state of the system changes, and an event is recorded. The other side is the read side. The query part retrieves accepted queries and retrieves the response from its view of the state of the system. The important part is that the query side does not talk directly with the system state, but it has a private view of that state that gets continuously updated. It's very important that the two sides remain perfectly isolated. So you have the command side, the write side, that only manages how the state of the system can change. And you can tune this side to be as fast as possible in accepting commands and writing events down. And you have the read side, where you can, that you can organize to be able to search inside your data as fast as possible and respond to your queries. They usually are two completely separated, two completely different technical entities. So you can tune each one for the job that it has to do. So we choose a quite classical ES plus CQRS stack. We were a JVM shop, so we went with Lightband Akka. That is based on Scala language, runs on the JVM. Akka gives you persistent actors. That is a very useful abstraction to work with event-sourced system. And it gives you a system that is easy to scale, easy to distribute on multiple tenants, and it's reactive. We went to Elasticsearch for the query side, because Elasticsearch is very good at making searches. And we went to Kafka for the event storage. You have to keep your events somewhere, and so we store it there. Kafka is distributed, it is easy to scale, so the whole stack was easy to scale, was easy to multi-tenant, and all the abilities that we wanted. Building the system went quite well. It was exciting. It was cutting edge. It was new technology. It was quite a difficult domain because it was very dynamic, but we knew the domain quite well. And it was an easy task, but with a good team you can do it. We managed to build the system and to bring in production to the first users. Everything went quite well. And then the fun starts. One thing that I noticed in working with event sourcing is that you can find really lot and lot of literature about your day zero problems, how to design, how to choose the technology, how to design your domain. You can find many tutorials, lots of documentation for your day one problems, that is building the system. After all, it's the documentation of the technology stack that you selected. But when you start taking it into production, when you start running it for some time, then it's very, very difficult to find commentaries about that. If you follow InfoQ, there was an article last week about another talk, more or less of this topic, and even that talk called for more information about this, more stories about event sourcing systems long-running in production. Because there are some things that happens that you maybe don't expect before. I run in some of these problems, and so I made this talk because I thought that someone else might be interested in knowing that. So, what was the first system? The first thing that I noticed is this: a change of state in an event-sourced system is an event. Well, that's the definition, okay? The problem is the vice versa is true. And moreover, that's all. This is a fundamental equation of an event system. Pardon me the poetic license. I know it's a fold left, not a sum, but it works better this way. The state of the system at time m is the sum of all the events from the beginning of the production of the system to time m. And this defines everything. There is no way to escape this. When literature says that every state change is an event, they mean it. There is no other way to change the state of your system. You have to keep this in mind when on Monday morning an operator of a client site calls you and to tell you, oh, sorry, the ATL job on the weekend went bad, and now you have 300,000 bad products in your data. You have to have some way to solve these kinds of problems. Because one thing that is that an event sourcing system is not good at is forgetting things. And this has another interesting angle. When we started building our system, the GDPR was not yet in effect. And we were lucky because we didn't have any personal user information inside the system. But if your system has GDPR concerns, you have to plan it well in advance, because it's very difficult to take out of an event sourced system something that has been put in, because of the fundamental equation. Every information, every event that got inside your system is reflected in one way or the other in your state, or you need it if you need to rebuild your state at some point. Second thing, well, it's quite easy to write. Knowing if you can read what you just wrote is another thing. That's a consequence of CQRS, really. Here is the system. So you are here, a user that issues a command. Your right side is optimized to get that command, evaluate, accept it, and write down the event that is the consequence of that command. And getting back to the user and saying, okay, your command has been accepted. So your write latency is easy to keep low and is very easy to measure. But before someone can read the effect of that command. The event needs to get in the queue, needs to get processed by the projection function, and needs to get indexed in the read side. And only then this user can query and find the result of the command. The bad news is that the read latency of a CQRS system is a very hard beast to tame. It's very easy to confirm the write, but the big problem is that you can keep the read latency low, investing in the hardware along the chain, but you can't pin it to a specific value. You can have, okay, average latency 500 milliseconds, yeah, but you will have some read that will take 2 seconds. You will have some outlier that will take 10 seconds because this is a distributed system, and sometimes some pieces fail, and some things, some communication get retried, and things like that. And the even worse news is that we found no solution on this problem. There is no way to keep read latency inside defined bounds. What we used to solve this was first, we started with what we call the finger-crossed timeout. That is, we hoped that 1 second would be enough to for the read side to index the event. And then our front-end side started working on accepting server-side events. And the definitive solution is that your read side can confirm, can send a signal to the front end that it has finished indexing. That's more or less the definitive solution, but of course, it's not an easy one. It replaces heavy burdens on both the back end and the front end to have that. So my advice is that you have to have, at the beginning of the project, a good talk with the UX designers and with the front-end designers. Sift through your use cases and see what are the most critical ones where a user issues a comment and wants immediately to see the results. Because that are the use cases that are most affected by this problem. Okay? Well, we're recovering our lateness. The projection function only reads events. And the funny thing is that the projection function is that bit that nobody talks about. The projection function is the function that keeps the query side up to date. It's this P box here. If you read tutorials and documentation about building CQRS systems, it's rarely separated from the write side. Usually, it becomes an integral part of the write side code or things like that. It's not always your case. In our system, for example, it was completely separated because it was reading events. And that's when you have an event sources system, that's all the projection function can be and can use. So your events must have everything that the projection function needs to update the read state. This can mean that sometimes you have to trade some hundreds of bytes of redundant data in the events instead of trying side channels or things that sidestep the event queue. Because the component, the projection function can't talk with the state. Believe me, I tried. You get very funky concurrency errors from that. And the ideal is that the projection function is just that, a pure function that goes from one event to updates on the read side. Be ready to use every bit of feature that your read side gives you. Elasticsearch, I really recommend Elasticsearch because it's very versatile, has lots of features that can really help you in this problem, in solving this problem. Everything you need, your event must not only capture everything that your domain prescribes that it needs to note down, but you must have everything that is needed to update the read event. Sometimes this means adding some redundant data. Okay. 4, if you have enough events, it becomes difficult to read them back. The premise of an event sourced system is that the state is the function of all the events of the story of the system. However, when you are 6 months in production, you better have lots of events. If you haven't, maybe you've chosen the wrong architecture because you didn't need event sourcing. But when you have lots of events, reading them back from the beginning might not be practical. So what usually becomes the equation of your system is something like this. That is, the state at time m is the sum of the snapshot of the state at time t plus the sum of all the events from time t onwards. This way, you don't have to read all the events back from the beginning, but you can start you can keep less events to read if you have to rebuild the state. The fact that the state of the system can be rebuilt reapplying all the events is a statement of feasibility, is a statement of possibility, not of feasibility. Even if you manage to keep your write latency down to one digit in milliseconds, when you have 500,000 events, you are already in the hour. Can you manage 1 hour of downtime if you are upgrading the write side and you need to rebuild your state? Maybe. But when you 1 year, you will have when you're 1 year in production, you will have 2 hours of downtime, and so on. That's why you need snapshots. Usually, every website technology gives you some way of snapshotting the state to manage this use case. If your website technology doesn't give you this, probably you need another one. Don't forget to store away the events, just in case. They are an effective backup of your history. And to delete the older snapshot, of course I've read this one because I was bitten by that, and because you don't need them anymore. This was when we got it, this was even more unexpected than the other one. The same thing is valid for the read side. Because even if you manage to keep your read latency down to 1 digit in milliseconds, it will be very, very hard to keep your read latency to 1 digit in milliseconds. And more than that, your read side is not optimized for writing. It's optimized for being queried. So if you had to issue all the history of the events another time, it will take you lot of time. And you probably won't have that time when you discover this. Even the simple system, even the simple event sourced system that is good for its domain will collect several tens of thousands of events in a few days. And each of that must make its way to the read side. As I said before, your read side is optimized for reading. And that's the opposite of what you need when you will have to repeat it, not if. So you should use snapshots also on the read side. There are many ways to do it with many technologies. And that will save you all the computational time that it took to build the read side, because you probably won't have it again. Okay. Well, I'm quite fast, even if we were late. So I have time for a bonus. Your MTTR matters more than your MTBF. You know what this means? MTTR is a mean time to recovery. It's the time you take to get back up if your system fails. MTBF is a mean time between failures. It's the inverse of the frequency of the failures in your system. It's much more valuable to be able to restart quickly than to try to stop and avoid every possible failure. A system built with event sourcing and CQRS is a distributed system. And a distributed system fails all the time somewhere. Maybe not completely, but some part of it is probably failing all the time. Given enough nodes, you will always have a node that is down. Some authors even say that a distributed system is never completely functional. It's always non-functional somewhere. With some thought, you can use this complexity as an advantage instead of an hindrance. If the pieces of your systems take very little time to recover from a failure, take so little time that no user can really notice a failure. For example, if a node of your system takes a half second to get back up, well, some user maybe will notice a little lag, but it's not a failure for him. So you're not failing. You are getting an uninterruptible service. If if you manage, so if you MTTR, if your time to recover is so small that no user will complain, because no user will notice, you may fail one time a minute, and nobody will notice. You don't have to spend all the energy and money that can be sizable to avoid that one failure per minute, because nobody will notice. Of course, I'm saying failures when you don't lose data. Some user will notice that if you lose data, even way after the fact. And don't think that a failure is just something that doesn't work. You may have to take down nodes to upgrade the system. So this is also, you also need this to be able to upgrade the system without interrupted service. So even sourcing is a valuable tool, is a very valuable tool. Be sure that you need it. It's complex to implement, but it may serve you well if you have the need that it serves. And remember that sometimes the less responsible moment in the agile sense is upfront. There are some things, even if you're working with agile methods, there are some things that you have to plan ahead, and that you better plan ahead. Okay? I need to say a couple of special thanks to my colleague Gabriele Favaretto, who taught me most of what I know of Akka, and to the scalability organizer, to Marca User Group, for being our sub-communities. And of course, to the Google developers for hosting this conference. Thank you. I'm a bit short on the time. If you have any questions, I'm here, or you may find me the whole day. Thank you very much.